Okay, everyone, welcome back to the webinar. We're going to go ahead and proceed with our presentations. This time we have the NEAMS Workscopes with presenter Dave Henderson from DOE NE. You can take it away, Dave. Thank you.
Okay, yeah, thank you. Thought I'd show my face to start. I'll probably shut down the video later for bandwidth issues, but thank you everybody for participating. Again, my name's Dave Henderson. I'm the program manager for the NE modeling and simulation portfolio. So we have two scopes specific to that I'll be covering in this session. So you can see my slides okay, I assume.
Yes, they are looking great on the screen. Thank you, Dave.
Okay, you bet. So this is where this program, the NEAMS program, I'll refer to in short, Nuclear Energy Advanced Modeling and Simulation, falls within the Office of Nuclear Energy. It's under Alice Caponides' organization and Suvel Schuppner, more specifically in the Office of Nuclear Energy Technologies. You have my email address there, and in the my contact information should be in the draft scope or the call ultimately, so you can get a hold of me or the technical POCs. So the mission for the Advanced Modeling and Simulation program, we're really trying to develop, demonstrate, and deploy capabilities that are useful to industry, whether the existing fleet or advanced reactors yet to come and fuel cycles. We are trying to focus on early stage R&D that is really solving problems that others aren't, and that are relevant to industry and also to the NRC, who's been a very important customer as well in our interactions. So we try to actively incorporate input and feedback from the nuclear industry and NRC in our work. You'll see some of the major technical areas, we call it, within the program: fuel performance, reactor physics, thermal fluids or thermal hydraulics, multi-physics, and app drivers is another area. Here I have workflow management. It's far broader than that, but those are some technical areas within the programs, as well as some of the codes that we actively develop, and you'll see some more about that later. So as far as the overall Office of Nuclear Energy mission space, there are three major areas that we contribute to: the existing fleet, advanced reactor, pipeline or deployments, and fuel cycle fairly broadly. I won't go into, these are kind of a very snapshot of some specifics within each of those areas. I'll hit the first two in more depth next. So as far as the existing fleet or issues that are relevant to the existing fleet, we're really trying to make sure that we're doing things that provide innovative solutions, especially to fuel and core performance issues. For LWR reactors, you see some specific issues and solutions there that we're aiming at within the program. We really would like to be developing tools that allow the LWR community to take advantage of accident tolerant fuels or advanced technology fuels, however you want to refer to those for different purposes. And to be able to address things like load following strategies, improved economics, things like that might be more limited with existing tools. Again, the existing fleet has very mature tools for their regulatory purposes and operation, but some of these evolving needs or uses or missions could really make use of advanced modeling and simulation techniques and tools. As far as advanced reactors or non-light water reactors, I should probably refer to as far as industry speak. I think there's a much larger space because of the there's not the data, the degree of data, the volume of data, and tools that are available for modeling those reactors. There have been modeling and simulation tools over the years for non-light water reactors. But as some of these move toward deployment and making greater use of the opportunities of those other reactor types, coolants or fuels or what have you, we feel like there are advanced modeling and simulation tools that could really help make the licensing case or demonstrate autonomous operation, for instance, feedback in a microreactor, things like that that could be really useful to the non-light water reactor space. So I wanted to present these this table of codes. If you had seen the presentation last year, we had these as well. The reason for doing this is, over time, the proposals that we would get would often propose things that had been a tool we were actively developing in the past, or maybe folks weren't aware of the full tool set that we're developing. And so I provide this as good examples for those proposing work. If you're proposing work on these codes, it's much easier for us to directly use the outputs of your work immediately and effectively, and to really be really directly contributing to the success of the program. So in some cases, and depending on the final wording of the scopes of work, this may not be required, but this should give you a very good idea of what we're actively working on and what would be most immediately beneficial to really incorporate the results of what you do in the scopes you would propose. I would note at the bottom in the chemistry area, this is kind of a rapidly evolving space for us. If you participated in the last session, the IRP that we are jointly pursuing with the Advanced Reactor campaigns, Brian Robinson presented. That's focused on MSR chemistry in particular. So this is a scope that we're hitting pretty heavily. We have Yellow Jacket identified in the non-LWR as a non-LWR applicable code. You'll hear other parts to that, whether it's the MSTDB database, properties databases that we're helping to develop, or the MOL code that Oak Ridge has been working on. We kind of refer to Yellow Jacket as the chemistry suite of codes for non-LWRs. So in case that's helpful. So I made mention a minute ago to the ultimate scope of work or topics that we put in the final FOA. I think this disclaimer has been made across the board. Until that funding opportunity announcement is put out in final form, things could still change. However, with these two scopes, I tried to capture almost verbatim what is currently in our scopes. So there are two under the NEAMS program specifically. This first one is on the improvement of low order transport methods. Matt Jesse at Oak Ridge is our technical lead in the reactor physics area. and so he'll be serving as the technical POC in this area. So this was really aimed at think about SPH factors or discontinuity factors that are used to correct for the uncertainties in transport methods. So the difference between what you would get from a Monte Carlo method that is very resource intensive. So in developing lower order, faster running methods, you ultimately have to do some kind of correction or feedback. So that's what this is aimed at. We're looking for new approaches, not so much improvements on SPH or discontinuity factors, but really hoping that the university community has some really good new ideas on how to tackle this problem of getting faster running methods with higher accuracy. We note that there's a particular interest in the effect of modeling on isotopic depletion history, and there's an interplay here between the transport method that's the focus of this call and multi-group cross-section generation and libraries that were the focus of a call last year. You'll see that note at the bottom. We're not looking for the cross-section generation in this call, but there is an obvious interface there on the transport methods and how you make use of those and how you could inform the development of those libraries from this side. So we really want to make sure that proposals provide detailed discussions of the methods and models that you're using. In the past, we get some kind of fuzzy scopes that sound kind of like a miracle occurs and you've got this solution. So we really want you to be specific about how you're going to tackle this problem, what piece of the problem it tackles, and the opportunity. So we'd really like to see the application of the method benchmarked against something like a Monte Carlo. We also another issue we've seen in the past is proposals that seem to be somewhat duplicative of other work that is going on or has gone on in the past. So we really want folks to be precise in that regard as well. Demonstrate that you know what the existing capabilities are in our tools and other tools that are out there, and how your scope differs, yeah, how it's different and how it improves beyond what's already out there. So that is the first NEAMS scope, NEAMS-1. The second scope that we have is for automated optimization in reactor core design. This was originally we were thinking of shape optimization specifically, and the difficulties that we've had there, and just a known need for improvement. We've broadened this a little bit in the scope as currently written, so that it's not so specific to shape optimization. So we're looking for basically any method, new method, to really come up with robust automated optimization in the reactor designs. You'll see the application areas of interest. Those are known areas where it gets difficult to optimize, particularly shapes, get that right and really get things accurate and efficient. So please consider those not as exclusive, but things that we know, areas we know could use such an application. We'd really like to see this incorporated in our tools, or at a minimum, a clear path to incorporate them in our tools, particularly the NEAMS framework. That's something where we could really make very broad use of the developments under this area, because then it can flow into a number of tools that we're using, particularly for advanced reactor development. So again, similar to the last one, it's really important that you demonstrate that you know the existing capabilities, which do evolve fairly quickly, especially in the NEAMS framework. So please identify that clearly, that you know what's already there, maybe even what's in development, and how what you're proposing advances and would fit with those tools. So I think, yes, that's my last slide for the two NEAMS specific scopes, and be happy to take questions. Thank you.
Okay, thank you, Dave. First question. Are you considering reduced order methods or just lower order methods like SPN, corrected diffusion, etc.?
I think I probably should defer to Matt if he's on the call, maybe to make the distinction, particularly in what would be most useful versus what we know to be out there. Is Matt Jesse available?
We have Matt on the call. Can you say something, Matt, to make sure we can hear
Yes.
you?
This is Matt Jesse. Can you hear me?
We can hear you. Thank you.
I would answer that question by saying the focus is on lower order transport methods, but we are looking for novel approaches that surround lower transport methods. I would think if ideas or approaches using reduced order modeling, I do think that that would consider to be applicable to this call, Dave.
Yeah, again, so I appreciate that, Matt. There's kind of keep in mind, there's kind of a time limitation on this response. So if the scope doesn't change at all, you can take that as our answer on that specifically. I think it could apply. Just make sure you're speaking to how it's a novel advancement, and that's hopefully that's where this discussion of what we were really trying to achieve there is helpful on this call.
Okay, thank you. Next question. For NEAMS-1, is the focus on developing a new code, or is it more on working to improve an existing code?
I would say that the focus is really on developing novel methods that either are incorporated in one of our codes or could be. I really shy away from development of additional codes. That just kind of complicates the landscape. I understand if folks have a preferred code that they would like to develop and demonstrate the method in. We're trying to be more open to those possibilities. again, for it to be more beneficial to the NEAMS program and broader use, I would at a minimum ask that it's very clear how that new method that you've demonstrated somewhere else could be incorporated easily into one of our codes.
Okay, great. Thank you. Excuse me. For NEAMS-2, does the optimization have to be core level? And will shape optimization of single fuel rod be considered?
Let's see. Trying to figure out how to address this. I think the real desire is that the application is within the core, although it could obviously, depending on what it could obviously be applied more broadly with different inputs besides temperatures and neutronics and whatnot. But the way the scope is currently written, that is the application that we're really looking for, is within the core. I guess I should just say that.
Okay, thank you. For the automated optimization, are there specific reactor types that you'd like to see them applied to?
No, we've not specified that. We're really looking for something that could be used more broadly. It could be demonstrated on any problem that shows where the automated optimization is needed and makes a significant impact.
Okay, thank you. There are already some low order transport solvers in NEAMS. Are you seeking some novel new methods or solvers which will run faster with acceptable accuracy?
I think in a word, yes.
All right, great. On NEAMS-2, is the focus to develop optimization methods or to demonstrate existing methods?
No, it's much more to develop, well, at least to, let me say this, either to develop new methods or to apply methods that may exist in other areas, whether it's aerospace or something else that have not been adequately or sufficiently applied in the nuclear area. I mean, again, I'd really like to see this be novel methods as opposed to just applying methods that we all know are out there.
Okay, great. Thank you. Let's see, at this moment, this is the last question. It seems to me that economic analysis of the entire fuel cycle tools is missing and not embedded in the existing computational packages. I was wondering if you could comment on that.
Okay, I'm going to interpret that question having to do with kind of broader fuel cycle analysis. And if I got that wrong, please go ahead and clarify. As far as the NEAMS program, we have really tried to narrow our operational space to multi-physics and multi-scale modeling and simulation. There's enormous opportunity, and it's ever growing for modeling and simulation more broadly, whether for fuel cycle analysis, regulatory use, our integrated energy systems program does some of that stuff as well. There's AI and machine learning opportunities, but we've really tried to focus on the multi-scale, multi-physics problems of reactor system modeling, just because there is so much to do in just that space alone that could really benefit either the existing operating fleet or advanced reactor deployment. So that's, as a program, that's why we've been somewhat limited to that space.
Okay, one more question just came in. Let's see. For new transport methods, does the code have to be used, the code that has to be used, is it MOOS? Okay, let me start over. Does it have to use MOOS as a framework for new transport methods?
I don't think we specified that in the scope. So if we haven't specified that, then it doesn't. That is where there is a lot of opportunity, but there is also opportunity within the Vera suite of codes. If there's an improvement there, that would be helpful as well. That's acceptable. It needs to be, again, it needs to be a significant advancement, and the problem is really when you go to pin by pin modeling of a large system.
Okay, I think that's it for these work scopes. We're going to just take a couple minute pause. Thank you, Dave, for your presentation and everyone for attending. At 12:30 p.m. Eastern Time, we'll resume with MS, NE 1 and 2. Thanks, everybody.
Thank you.